Well, I have the pleasure of introducing our next speaker here, Professor Xiong from UC San Diego. Uh, Wei is a professor and Kent Wilson Faculty Scholar in the Department of Chemistry and Biochemistry at UC San Diego. Received his undergraduate degree in Peking University in 2006. Then went on to join Martin Zane's group at Wisconsin-Madison, completing his degree in 2011. And after that, he had moved to University of Colorado at Boulder, where he began to develop tabletop XUV sources for ultrafast measurements. In 2014, he moved to join the faculty at UC San Diego, where they are developing these nonlinear ultrafast techniques to reveal molecular structure and dynamics of different systems. So Wei, of course, has won many awards here. I won't list them all. I'll just note a few. A fellow of the American Association of Advancement of Science, and most recently, one of this year's uh, American Physical Society Fellows of the Division of Chemical Physics. Wei, the floor is yours.
Thank you, Nathan. I want to thank you, Nathan and Jake, for your nice invitation. And also, I want to thank the previous speaker for the nice talk on the theoretical work of molecular quantum science. So what I like to focus and tell you a story about is the role of energy disorder in polariton dynamics. Before I start, I just want to thank the people who did the work, specifically a big thank for Dr. Tianlin Liu and also Guo Xinyin, who actually performed this specific research I will focus on today, and also for the funding source mostly from Air Force as well as NSF on those work. So I believe perhaps many of you are not familiar with the term, or if you're not familiar with the term of polariton. So it's basically a hybridized state between two resonances. One resonance that we as chemists are very familiar with. So those are the atomic or molecular resonance. And when you think about this type of resonance, we think about having electrons just orbit around the nuclei in a very classical picture. And when those particles repeat their trajectory, that they form a resonance. So another resonance we're going to deal with are the photonic resonance. And that's also very similar in terms of how particle retrieve its trajectory. So basically, you can consider as photon being trapped in a very, very small volume where the photon actually somehow retrieve its own trajectories back and forth. As a result, it can form a very narrow resonance in certain frequency. So polariton is not a new topic. Indeed, in the world of physics, people have already think about what's going to happen if people mix the atomic resonance with the photonic resonance together. And what they found or concluded was that if there is enough dipole coupling between these two resonances, then it is simple a 2x2 Hamiltonian system that usually referred as Jeans-Cummins model. And if you diagonalize this Hamiltonian, it's very similar to what we see in the molecular orbital theory, so that we can generate two new eigenstates that is referred as upper and lower polariton, where each of the states are a hybridized state between the matter and also the photonic side. And it was actually coined by John Hatfield with the term as being called polariton. So and physics have actually shown a lot of interesting phenomena when they have this sort of polaritonic system, such as giant nonlinearity and also change of dissipation properties, stuff like that. And in the past decades, this has caught attention of chemists, and one of the question is like, well, can we actually form a similar type of hybridized systems in molecular systems when you put molecules inside of a cavity? So the short answer is yes, you can do that. However, with one difference. So the difference is that for a molecular resonance, such as a molecular vibrational mode, the transition dipole moment compared to a atom such as Ribram atomic state is much smaller, and in that case, that you can't actually have the photonic mode to strongly couple to a single vibrational mode of a molecule to form the so-called polariton. Instead, we need to have a lot of molecules inside. And in this way, you can still reach to the strong coupling regime, but this is a collective strong coupling to the cavity mode. Therefore, we need to change the Hamiltonian a little bit. The change is that instead of having one atomic state to couple to the cavity mode, we need to have many of the molecular states to couple to the same cavity mode, where each of them couple to the cavity mode through a single molecule light matter dipole coupling strength. Well, the good thing about it is that if you diagonalize that Hamiltonian, you'll still be able to see two polytonic states that are still hybridized between the cavity mode and the molecular vibrational mode. So that's a good part. So that means the polariton concept still exists with one drawback or caveat, that is there's a lot of dark mode there. Okay, so I'll come back to the dark mode momentarily. But in terms of the, how to think about the polariton, how it manifests is if you take a spectrum of the polytonic system, you will likely to see like two split bands now, where the separation between these two bands are the so-called Rabi splitting, where it characterizes basically it corresponds to the collective coupling strength. So that's also how experimentalists to characterize how strong their strongly coupled system is. However, that a better way to see it is in the time domain, which is that if we put energy into either the vibrational mode or the cavity mode, you'll find that those energy or excitation will not stay inside of those modes. Instead, they will fastly exchange energy between each other. And that's a manifestation of that, those vibrational or cavity state are not good eigenstate anymore, because we can't really define where the energy or excitation stay. So that's why we need polariton mode. But this is the hallmark, one of the hallmark for polytonic state, that is the fast energy exchange, which will come back later. So in summary, the property of polariton can be summarized as that it's a hybridized light matter state. Therefore, it has property of matter as well as property of light. And because of light is more delocalized compared to matter in this case, so the whole polariton have a delocalized property, like a delocalized function. And as you can see here, just like when you form new molecular orbitals, or like those J aggregates, we also form new eigenstate with modified energy. So because out of those characters that people have thought, would it, or have the question to answer, would it actually change chemical reactions? And there are some examples. In the first example, that when the French group, Thomas Eberson's group, put this specific molecule that's called as R inside of the cavity, it can see that while outside the cavity, the molecule prefer to break the silicon carbon bond, but now inside the cavity, they actually see that it break the silicon oxygen bond more preferentially. And overall, all the chemical reaction rate has also been changed. And a few years later, the group of Blake Simpkins at Novel Research Lab in the US also show a different reaction, where that they, by coupling to different vibrational mode, they can see this bimolecular reaction would also have a reduced chemical reaction rate. So this potentially can bring a new paradigm to actually control chemical reaction rate and selectivity. However, there is one concern that a lot is related to this dark mode that we just talked about. So when I tell you that we can reach to collective strong coupling, I didn't tell you the number of molecules that is needed to reach to collective strong coupling. Practically, that one need to put on the order of 10 to the 7th to 10 to the 11th of molecules inside of the cavity to reach to collective strong coupling. However, when you diagonalize the Hamiltonian, you will only generate two new eigenstates that are the polariton mode, which means the rest of n-1 state, which is still on the order of 10 to the 7th, 10 to 11th, all the dark mode. So a fundamental question here is, yes, we can see those polariton mode are magic. How would it actually influence the overall system, where that they are the minority state, where the majority are the so-called dark mode? So it seems a little bit confusing or hopeless here, but I want to remind you, in reality, sometimes this type of thing can happen, such as, there are great people like Steve Jobs and Bill Gates and many others. they are, single individuals, but they can really influence society, where there is the rest of us here that we are the majority, right? So I want to know whether this is also the case, or in my group, we want to know whether this is also the case for a chemical systems. But specifically, what we really want to actually address here is to understand the vibrational dynamics of polariton mode versus the dark mode. Because if you think about the chemical reaction, it is a system. It's one of the fundamental questions people want to answer is how would the original energy put into the molecular system dissipate inside of the molecule, because that is important to determine how a chemical reaction would happen. So that lead to an introduction of the experimental tool that we will use, that is coherent two-dimensional infrared spectroscopy. It's a technique developed about about a little bit more than 20 years ago, that initially developed to study structures and dynamics of a lot of biological systems. And we found it's also we adapted into polariton and found it's a really powerful tool to study it. So specifically, it involved basically three pulses, three pulses to trigger coherence, just like what Kadei said, that when you have a laser pulse coming in interact with the system, you can create a coherence, and this coherence would dephase, where that we can add this quantum coherence with another laser pulse to a population state and relaunch this coherence again with the third pulse, where this last coherence would emit an optical signal to be detected. And we can scan the time delay between the first two pulses to characterize the first coherence. So by launching those two coherence, we can then use those coherence as tags to really to follow the energy transfer or energy changes between different quantum state. So specifically in terms of polariton system, there is one upper polariton and there's one lower polariton. So when we take polariton spectrum, 2D spectrum, we can see two diagonal peaks that correspond to the upper polariton and lower polariton. And then you will also see other exotic peaks, such as those peaks at the corner of this box. And those are the so-called cross peaks. In the world of 2DR, when you see this type of peaks, it usually indicates a energy, there's some sort of like correlations between those different quantum or molecular states. And therefore, in the context of polaritons, when you see those cross peaks, as I'll show you later, it basically indicates there is an energy transfer between the matter component of the upper and the lower polariton. And then the second benefit of it, as you may notice, that there is also additional peak in the middle of those spectrum, and those correspond to actually the energy of the dark mode, because those are unmodified energy, energy state. And therefore, you can see 2DR has this ability to not only follow the polariton state, but also track the dynamics of dark mode, which is the power of the technique. So with this, I will show you three stories to answer the question of what polariton are really special in terms of controlling chemical reactions. So the first one is the first question we try to answer is what polariton are really good at. So we designed the experiment to put two types of tungsten calcium carbonyl inside the system. One of them is isotope labeled. So in the regular cases without any cavity and strong coupling, you can see those are just two molecular vibrational peaks, but you don't see any cross peak indicating there is no energy transfer between those modes. And that's known because of inside those liquid phase system, energy usually just quickly dissipate out. However, once we put them inside of the cavity, you can see this new cross peak emerge between the upper and lower polariton mode, indicating there is an energy transfer happened between them. And this was work led by my former student, Dr. Bo Xiang. So after this work, we showed that what polariton is really good at is that it can enable new vibrational energy transfer pathways between molecules that would otherwise not exist in the typical liquid phase system through this strong light matter coupling. But the next question we'll try to answer is then how it would influence a chemical reaction. To address that, we look for a specific system that is simple enough for us to really track the fundamental chemical dynamics. And this system is iron pentacarbonyl, which can undergo a so-called pseudo rotation. So in this process, the axial group of the metal carbonyl would merge into transform into a equatorial group and vice versa. Um, through this course of reaction, that these chemical species would also overcome a a barrier that is about 3 kcal per mole. So the whole thing happened at ultra-fast timescale. However, as you can see, this would actually represent the simplest picture of a simple elementary reaction. And it's even better, the axial mode and the equatorial mode, actually each of them have their specific vibrational energy transition frequency. Therefore, as they morph and exchange their role, they would also carry out energy from the A mode to the E mode or E mode to the A mode. So we can use 2DR to track it. Indeed, that's what Chuck Harris group did, and they characterize all the dynamics inside of outside those cavity. Our question very easy: what happened inside the cavity? So by actually putting it into the cavity, we can follow the cross-peak dynamics between the upper and lower polariton again, which is the yellow trace, and compare it with the dynamics outside cavity, which is the red scatter line. So obviously, you can already see for this cross-peak that when it involves the polaritonic state, the energy exchange dynamic become faster again. So the cross-peak dynamic become faster. And even more, that using 2DR, we can track how these dark mode dynamics evolve, which this dark mode peak that I highlight here directly correspond to the energy transfer between the A mode and E mode without involving the polariton and only involving the dark mode. And those are the gray dot traces. You can see the gray dot trace and the blue and the red dots, they pretty much overlap with each other. So the take-home message here that, well, polariton can actually change the dynamics of molecular systems, the dark mode cannot. And that actually agree with the theoretical prediction that dark mode are just, those normal molecules. There is a little bit, details that chemical physics actually really care about. That is, there are actually two magnets that contribute to this cross-peak dynamics. I told you one, that is this pseudo-rotation. Another channel is IVR. So I'm not going to go to details, but you can see for IVR, it is any transfer between two orthogonal vibrational mode. Therefore, you can imagine their anisotropy should start with negative 0.2. However, for the pseudo rotation, you see in the molecular frame, even though it starts with the E mode and end up with the A mode, the net dipole moment is always pointing up in this molecular frame. That means this is an energy transfer between two modes that is parallel to each other. In this case, the anisotropy equals to 0.4. So we went ahead, measured the anisotropy for the outside cavity case and for the polariton case. You can see the anisotropy is dramatically different, and we have to feed it using some a complicated kinetic model to extract the actual dynamics. And the conclusion is actually for outside the cavity case, it is dominated by the pseudo rotation, but still have an IVR component where that the IVR component is accelerated again. So energy transfer is accelerated by putting molecule inside the cavity. At the same time, the pseudo rotation is also slowed down a little bit. So the second conclusion that I want to show you is that by mediating energy transfer either between or within molecular system, it sometimes can actually hinder competing dynamic process that involve chemical reactions. However, this influence can only occur with system such as that's involving the polaritonic channel, not the dark mode channel. So the last one, which is really what I want to focus on today, is the role of energy disorder. Why that we want to focus on that? Because in the first two systems, we chose very homogeneous system to study because we want to reduce the complexity. However, even in our own work, we find that in some systems that even though that we reach to strong coupling, such as this green trace, that we cannot actually modify dynamics. We have to increase the coupling strength even further to actually see the change of dynamics. And Kevin Kubarich group and also Adam Dunkerberger group showed that if you take 2D spectrum in an inhomogeneous limit chemical system, they can pretty much explain all the 2D spectrum or majority of the 2D spectrum through the so-called filter effect. What they mean is basically that inside of this system, the molecule just behave like a bare molecule. So we want to know what is the difference here, because previously we studied a homogeneous system, where here that system are inhomogeneous. And to give you a little bit background, that previously people don't consider energy disorder, because of there has been one really nice paper to already explore the role of energy disorder. This paper basically concluded as you increase the energy disorder in homogeneity, you will enable the dark mode to be a little bit bright. However, the polariton spectral signature still remain the same. Therefore, people, including us previously, always take this as evidence as the formation of polariton is robust against the energy disorder. But because of those additional experimental evidence, that we start to question this. And my postdoc Tianlin Liu and Guo Xin, they actually went ahead to explore that a little bit using this Tavis Cumming Hamiltonian that I showed you before. What they did is they basically make the matter state to be a little bit inhomogeneous. For example, here that they make the inhomogeneity of the molecular transitions, which is the blue line here, to be 24% of the Rabi splitting. In this case, you can still see that we can form polaritonic state. They further make it to be even larger, that is about 70% of the Rabi splitting. Even in that case, you can still see we can get the polariton spectrum. However, the difference is actually about is hidden in the polariton wave function. As I plot you here is the state in two different basis set, either in the polariton basis set or in the molecular basis set. And as you can see here, that if I excite the polariton, here the polariton excitation is delocalized between many molecules. However, if I excite the dark mode, that my dark mode excitation is only localized to this molecular vibration mode that share the same frequency. So this diagonal line indicate a signature of localization. This vertical line indicate a signature of delocalization. But the polariton delocalization nearly diminished if I increase my inhomogeneity to the 70% mark. You can see the entire system is all lying along the diagonal, indicating most of my excitation are localized. We further explore the map by using the inverse partition ratio that where in this case, 1 indicate delocalized and 0 indicate localized. As you can see, this is the criteria for strong coupling. On this side, this is weak coupling. There's no polariton. On this side, this is all strong coupling. However, here, even when I form the polaritonic system, it's still a localized polariton. Only if I increase my coupling strength to be 3 times more compared to the strong coupling criteria, I can push the polariton to be delocalized, to be a delocalized polariton. So why does it matter? And we want to explore that. We find a system that is a phenol system. When it's very diluted, you can see a single vibrational peak of the OH mode that without hydrogen bonding. When we put a concentrated liquid phase solution, then we can see additional peak showing up that indicating a hydrogen bonded species. In either case, that you can feed them with Gaussian peaks, indicating there is a large amount of inhomogeneous brightening. However, if we lower the temperature a little bit, we actually see 2 nice Lorentzian peaks, and through calculation and low temperature investigation, that we assign them to be a singly hydrogen bonded species and a doubly hydrogen bonded species. Nevertheless, this gives us a really nice system to compare the the influence of inhomogeneous brightening, because this is the same system. We only tune one parameter, that is the temperature. We can make it either homogeneous or inhomogeneous. So we can make them to form into a nice polaritonic system, as I show you here, where that we can keep the coupling strength also to be the same. So long story short, so this is the 2D spectrum that we use. Long story short, that if we study the liquid phase system, the inhomogeneous system, when we measure or extract the cross-peak dynamics and diagonal peak dynamics, we see in both systems, no matter if it's inside or outside cavity, the dynamics look the same. Nothing changes. But if we change it into the solid homogeneous system, you can see the solid state cross-peak dynamics is accelerated about 3 times compared to the dashed line, which is the regular outside cavity case. So the dynamic is accelerated when the system is homogeneous, but does not change at all when the system is inhomogeneous. All right, to further see what actually has been accelerated, there are again 2 different mechanisms can change the 2DR dynamics. One is conformation exchange. So that means the doubly hydrogen bonded can basically have one hydrogen bond break and form a singly hydrogen bonded species. Or that the doubly hydrogen bonded and singly hydrogen bonded species can just easily transfer energy between each other. Again, we can use polarization to study it because in the first case here, that when you break a hydrogen bond, there is a finite dipole moment change is about 120 degrees. But here, the chance for energy transfer between different angles is more random, as we confirmed in the simulation. And indeed, when we measure all the anisotropy, in many cases in our system inside the cavity, we find the anisotropy always start with 0. So that means in this case that the polariton enhance the energy transfer again. And it's very interesting because you can see, I told you in the liquid inhomogeneous case, no matter how we increase the coupling strength, we just see that the exchange dynamics remain the same. But in the outside case, well, if we have a slightly smaller coupling strength, the dynamic change back to the same as outside cavity. Only if we start to increase to a certain level, we see the change of dynamics. And why is that the case? That is the second to last slide. So if we plot all the coupling strengths and also the inhomogeneous full width half max of all the data point that we studied onto the delocalization map, it becomes very clear. It shows that if that in the case of inhomogeneous broadening, that all of my polariton are in this space of localized polariton. Where only for the homogeneous case, when we have high enough coupling strength, we can push the polariton to the delocalized polariton state. And that is important because of us, what Jianshu Cao actually predicted a few years ago, that in a general resonant energy transfer case, if one can form a delocalized coherent state, then you can enhance the energy transfer rate by exactly the number of delocalization you generate. And in our case, it means that if we form the polariton, only if we can form a delocalized polariton state, we can enhance the energy transfer. So that's the last take-home message I want to show you. That is, in the polaritonic state, we do need to consider energy disorder. It has a detrimental effect, and the way to overcome it is either engineer and reduce the energy disorder or push the coupling strength to be even higher. With that, I want to thank you for your attention and happy to answer any questions.
Thank you for a fantastic talk. You are able to type your questions in the Q&A feature, or you could raise your hand as well. I will unmute you and you can ask your question. Okay, maybe to kick things off here. So this generally seems IVR and disorder kind of go hand in hand in terms of decelerating the dynamics and chemical reactions. Is there a driving force for acceleration that's kind of just, I guess, commonly kind of just observed in different studies and maybe even your work as well?
Acceleration of IVR, energy transfer, or acceleration of chemical reaction.
Of
Because those
chemical
are
reaction. Yeah.
so it's very interesting. So in most of the observation or report of this polariton chemistry, most of them are slowing down. And especially if you count the one that has been reported to be reproduced by other. There are a few that is reported acceleration. that is still there was some theories that can explain acceleration due to the change of usually it's like a resonance effect. So there are acceleration, but it's less understood, I would say. In terms of deceleration, based on our work, if that polariton can mediate energy transfer, then it basically just quickly dissipate the driving force for chemical reactions. Exactly that connection that remain to be further tested by further experiment, and we are currently doing that.
Very nice. Good. Okay, so let's see. You're welcome to raise your hand to ask a question, or you can also type it in the chat here. Okay. Well, I'm not seeing any additional questions here. If you're furiously typing, now is the time to hit enter to ask your question. Um, Otherwise, I would like to thank, of course, Kade and Wei for giving excellent talks today and joining us in the seminar webinar series. As we look ahead to what's next here, so we will pick up again the DCP webinar in April 10th. In March, of course, we hope to see you at DCP sessions at the American Physical Society Global Physics Summit. Until then, take care, everybody. Happy Valentine's Day. Oh, and we do have a question. Yes. So this is from Anonymous. A basic question: why can two-dimensional IVR, two-dimensional IV observe energy transfer to dark mode from a polariton mode? Is it due to disorder?
Really good question. So in terms of technique-wise, so typically I didn't cover that part. So typically a 2DR, a dark mode, really should remain dark and cannot be seen by any spectroscopy. But due to this energy disorder, that it make the dark mode to be a little bit bright. So in 2D spectroscopy, one of the axis is actually a absorption axis, the other is a transmission axis. So we can actually really see those excitation of dark mode through the absorption axis, and therefore we can actually follow the dark mode, and then it doesn't actually transfer. Yeah, then we can follow the excitation of the dark mode. And then to further answer your question that why we can see the energy transfer to the dark mode from polariton mode, there are a few things I didn't cover. That is, there are two ways we can follow dark mode. One is through this so-called Rabi-Slitting contraction that is due to excitation of dark mode instead of polytonic response. So what we do is that we track how what is the Rabi-Slitting basically how it changes as a function of time, and through that we can back calculate how many dark mode is excited in a certain state, and therefore we can see how the polariton transfer to the dark mode. That's usually how we do that, and sometimes we also track it from the 1-to-2 transition of the dark mode due to if that overlap with the transmission window of the polytonic state. I hope that answered your question.
We had another question just come in here as well. The question reads, what is the role of the initial conditions in the molecular ensemble for the polariton dynamics?
So I'm not quite sure what it means here by initial condition. So if we are saying whether the initial is about which initial state that's been excited, I think it's really, really important. So based on all the study that I showed you, if we excite or prepare a polytonic state that is delocalized, the dynamics, it can enable different new additional energy transfer channel, where that if we excite those dark mode, then nothing happens. And then there is a question also about what if you don't excite anything, you don't send laser pulses, and you just thermally excite it. Then in that case, one can basically assume that a regular thermal population. And in that case, I would think unless that the polytonic state can really drive the a certain dynamics by order of like 3 to 4 order of magnitude higher, compared to the regular dark mode, then you wouldn't see any change. I hope that answered your question.
Yep. Vasil says, yes, I meant excited versus ground state. Thanks a lot.
Yeah, thank you.
Wonderful. Well, thank you again for two wonderful talks, and I look forward to seeing everybody in a month at the APS meeting. Take care.
Yeah, thank
Thank
you,
you.
Nathan, Zach, to organize it. Bye.
Mhm.